true. And we started out almost 3 months ago as strangers. Now we're all friends, right? It's wonderful. And in the meantime, actually, we learned a couple of things about atoms and molecules. And so we'll just try to do the best we can next Friday when we will meet once again in a slightly different setting. And you guys will be doing the exam, and I'll be pacing around and grading your exams afterward. Okay, so this lecture is just reviewing some additional points that we didn't get to last time. So I'll go over some of the things. I had a couple of issues. And then hopefully there will be some time left for questions. All the other questions, I think, should be addressed and will be addressed. Let me see if this works. During Monday's review session. And this picture shows a person who studied too hard. Okay, so studying is of course important. You want to make sure you are in good shape, but don't overdo it. I've had folks that think that before they do an exam, they have to study through the entire night and don't sleep. And I don't think that's a good way to do it. Okay, so because this is what you'll look like, and this is what your exam will look like too. Okay, you need your brain. Your brain needs rest to function well. So make sure to attend the Monday review session at 7 o'clock. It's the final service that we offer. Next week, because it's finals week, a very odd week, it's not a regular week, so there will be no office hours. Those of you who visit my office hours sometimes, they won't be there. So this is the last kind of opportunity to interact with your teaching team beyond the Piazza Forum, which will be open 24/7. Okay, so we will keep conversing there if you have any questions. Okay, so let me go back a little bit and talk about these kind of questions, where we looked at molecules and we looked at ways in which to write down the formula, molecular formulas of molecules like this. This is a line structure, and we should be able to draw line structures, not as complicated as this, but we should be able to write down the molecular formula from this. Okay, the chemical formula. So, the molecular formula or chemical formula is something that says C, X, H, Y, and so forth, right? So you have to count the number of atoms of each kind and then write that down in a molecular formula. That is what you have to do. So it's going to look like this. Let's first look at the C's. There are 8. Why? Because there's one here, one there, one there, one there, one here, one there, one there, and one right there. This end point is a carbon atom with 3 hydrogens attached, remember? So that's a total of 8. The next element you'd like to put down is the H, the hydrogen. There's one here, one there, one there, 2 here, 2 there, none here, none there, none, 1 here, and there's 3 there. That's a total of 11. Okay? Then there's 2 more elements. In this case, there's 1, 2, 3 oxygen, and there is 1 nitrogen, and then you're done. What should you not do? Well, we shouldn't start writing here HO, C, H2, C, and then just like have this long list of elements in there. No. Okay? This is a molecular formula. We're not asking you to invent your own fantasy condensed structural formula of a structure like this. You will not succeed, and you will see an ugly red cross in your answer on the exam. Okay? A molecular formula looks like this. It is compact, it only lists the elements with the count of each element. That is the answer. Another kind of question is, I list a condensed structural formula. This is a condensed structural formula. This is not called the molecular or chemical formula. It's called the condensed structural formula. Okay? This we should be able to translate into an actual line structure. Okay? So let's do that. First, let's have a look at this thing when we start to read it from the left to the right. I see two CH3 groups. The CH3 group looks like a stick. Okay? These two sticks are connected to this carbon atom, which also happens to have another H, which I will not draw because H's are not drawn in my instructions. So this carbon atom here has one CH3 group attached, another CH3 group attached. That's why there's two here. One H and one carbon next to it. This carbon has an oxygen and another neighbor, which is carbon. This carbon has H2 and OH. So it looks like this. Okay? This point here is that carbon right there. It has two lines. Those are the two CH3 groups. This CO is this one here, C with one oxygen attached. On the other side, it has one carbon and another carbon. This is the carbon with the oxygen. On one side, it has this carbon. On the other side, it has that carbon right there. Okay? This last carbon, all the way to the right, is this carbon, the last carbon in the chain. It has one H, sorry, there's two H's, 1, 2, and an OH group, which is this guy right here. Alright? So this is very systematic. It's very systematic. So make sure you are able to translate this into a formula like this. We've done many of these, and you can go back to the midterm, to the first midterm. Remember, there's 4 midterms there with answers for you to look at. Okay, so it's good practicing material. I'm going to cover the answer, try to see if you can find the answer, and to see if you're in good shape. Okay, let's now move on to precipitation reactions. In particular, let's look at the stoichiometry of these things. So a typical question could go like this. 1 mole of an aqueous potassium sulfate solution reacts with 4 moles of aqueous barium chloride solution. And then I have to calculate the amount of grams of the precipitate. Typical question. 2 solutions are given, okay? The molarities are not given. The volumes are not given, the molarities are not given, but it is given how many moles I have. That's great. I already have moles. That's what I want. I want moles because moles allows me to make mole ratio conversions, okay? Conversion to the mole ratio. I have to calculate the amount of precipitate formed. So I have to calculate how many moles of precipitate do I form, then convert moles into grams. So first things first, I want to write down a balanced equation. I just have to translate this word into a chemical formula. Potassium sulfate. Okay, potassium is K, sulfate is SO4 2 minus, and it is K2 SO4 2. Sorry, SO4, that's right. This one here, barium chloride, barium is 2 plus, chlorine is -1, so it's BaCl2. Okay, so here it is, K2SO4, that is potassium sulfate. This is BaCl2, that is barium chloride. You can make 2 new combinations, okay, namely potassium with the chlorine ion, that will not form a precipitate. Okay, because chlorine dissolves well with many cations, and in particular with cations that are of polymetals. Okay, so your polymetal ions dissolve with almost everything. So this guy will not form a precipitate. Therefore, potassium chloride is fully dissolved in solution. Therefore, the only possibility for the precipitate is barium sulfate. And indeed, sulfates typically dissolve well, but not with barium. Barium was an exception. On your table, you can read that. So barium sulfate is a precipitate. It gets an S, while this has an aqueous symbol. Okay? So this is the equation. It's actually the molecular equation. Okay? Given in terms of molecules. Then I'd like to determine the limiting reagent. So I already have the number of moles. And so I'm just going to do quickly a comparison with the balanced mole ratio versus the actual mole ratio. So the equation says this. 1 mole of potassium sulfate for each 1 mole of barium chloride. That's what I need. Okay, that is 1 to 1. Let's look at the actual numbers. This is easy because the number of moles is given right there. Just have to divide one by the other, I put, of course, potassium sulfate on top. How many? 1 mole of potassium sulfate, 4 moles of barium chloride, so it looks like this. And that is less than 1, and therefore, the numerator is the limiting reagent. K2SO4 is the limiting reagent. Right? So, how long does it take to determine the limiting reagent? It doesn't have to take very long, right? Because this is what you have to do. One ratio, another ratio, look on which is bigger, boom, you know which one's the limiting reagent. Don't make that, 30-minute search on your exam. This literally takes 1 or 2 minutes to figure that out. Okay? Once you know the limiting reagent, of course, determines how much precipitate you form. Determines the amount of the product. Because what I'm going to do is I'm going to take the number of moles, in this case 1, of the limiting reagent, which is K2SO4. 1 mole of K2SO4 I'm going to convert into moles of the product. The product is barium sulfate. Okay? The ratio between barium sulfate and potassium sulfate is 1 to 1. That's what the equation says. For each 1 mole of potassium sulfate, you make 1 mole of barium sulfate. And therefore, 1 to 1, and now I convert this 1 mole of potassium sulfate into moles of barium sulfate. Once I know the moles of the product, I simply multiply that by the molar mass to find grams. Okay? And here's the molar mass of barium sulfate, 233.43. So you can see, if you look at the units of molar mass is grams per mole. This mole very nicely crosses out. So you convert your answer into grams of barium sulfate. The answer is 233 grams of barium sulfate. Okay. Let's do another one. Let's do an acid-base reaction. Okay, the question, this is a typical question, and I think something similar actually appeared on the midterm. How many milliliters, that's a volume, so what is the volume of a particular solution that I have to add to an existing basic solution, sodium hydroxide, to neutralize this solution? Okay, so let's visualize it. Let's visualize the situation. If you read a question like this, you want to make sure you understand the physical situation. I have a bucket with, what is it? Sodium hydroxide, which is a basic solution. The basic solution has a volume and has molarity. Is that given? Yes. It's not exactly given, but it's given how many grams there are. So I know how many OH minus ions there are in the solution. The question is, how much of an acid do we have to pour in there? What's the volume of the acid we have to pour in that bucket to neutralize all the OH minus ions? That's the question. Okay? The acid that you're going to pour is perchloric acid. So a reaction is going to take place. The H pluses of perchloric acid are going to be interacting with the OH minuses, neutralizing the OH minuses, and you are neutralizing the entire solution. Okay, the first thing you'd like to do is to balance this equation. This is sodium hydroxide. Okay. Oh, interestingly, it is solid. So in a bucket, there's not even water. Just a chunk of sodium hydroxide. It's solid. And you have to pour acid on top to neutralize that. So this has an S here. The fact that this is not in solution makes no difference for the reaction that's going to take place. Okay? Both of these are strong bases and acids. So this is a strong base, this is a strong acid. This H plus will attack the OH minus, whether it's a solid or in solution, it doesn't matter. Okay? So this H plus will attack this OH minus to form water. And then the other ions are ClO4 minus, which is the perchlorate anion, and the sodium plus cation. These two things remain happily in solution, both dissolve very well. So this is your rest ions, if you want. So the actual reaction simply is this H jumps on the OH and forms water. Looking at this, I can see immediately that for each OH in my bucket, I need one H plus. So that's 1 to 1. Okay? So what I'm going to do is this. I say I need to neutralize this OH minus part of this solid. So in order to do that, I need to know how many of the OH minuses are there. Do I know that? Yes, I know, because I have here a mass, and I can convert mass into moles. So let's do that. 2.5 grams. This is the mass of sodium hydroxide. And I get 0.0625 moles of sodium hydroxide. That's how many moles of sodium hydroxide units I have. What I want is to know how many OH minus I have. Okay? But that's the same, because each sodium hydroxide has only one hydroxide. That means you have the same amount of hydroxide ions that you have to neutralize. Okay, so this is my target. I have to get rid of this by adding H pluses. So how much do we need? Well, I have this many. They react 1 to 1. Okay, so for each OH minus, I need one H plus. So this OH minus is crossing out. And I convert into the moles of H plus. And each HCl4 has one H plus to offer. Okay, so I can convert from H plus into this compound here, perchloric acid. Each 1 mole of perchloric acid has 1 mole of H plus. So what I do, I convert from OH minus to H plus to HCl4. Okay, so this is basically just 1, 1, 1. It doesn't matter. It's all the same. I need this many moles of perchloric acid. I calculate the number of moles of OH minus. I can calculate how much H plus and how much HCl4 I need. HClO4, sorry. So this is the number of moles. It's not the answer yet, because I have to tell the person that's grading my exam how many milliliters I need. So I have to convert number of moles into volume. Moles to volume. Is that a conversion you can make? Yes, you can if you know the molarity. Molarity given? Yes, it's given. That means I can do one step to convert moles into volume. Okay, so let's do that. This is moles. Let's convert it to volume. I'm going to use this. You have to divide that molarity. Why? Let's look at the units. Molarity is mole over liters, but I have to divide by molarity so that the mole appears at the bottom and the liter appears on top, because I want to go to volume. Okay, so this number divided by molarity gives me something in terms of liters. I want milliliters, so I do a last conversion here, which is 1 liter equals 1,000 milliliters, and I get my answer in milliliters. This is the final answer. So, what I've done, determine how many moles of OH minus, how many H plus, how many perchloric acid units do you need? That number of moles can then be converted through the molarity into volume, and that's the final answer. Typical question, make sure it's not a hang-out for you. Okay, the redox. Redox reactions. The last topic. And clearly, there's sometimes a bunch of steps you have to take. As long as you take those steps consistently, you'll be in good shape. I know people are, wrestling with the homework a little bit and scratching their heads over, this doesn't make any sense. It doesn't add up. Well, typically, there's small mistakes. Either you overlooked a charge, you added 1 electron as opposed to 2, or you forgot that the hydrogens actually have a plus charge. You add protons on one side, you add plus charge, you have to compensate through adding electrons, right? So usually mistakes are in such details. And you can get them out of the way by practicing a couple of times to make sure that you get this down. Okay? Here's an example. Solid sulfur reacts with sodium nitrate in an acidic solution, and it forms sulfur dioxide gas and nitrogen monoxide gas. I have to find a balanced equation through half reactions. So let's do that. Okay, so I'm going to write down just what I read. Solid sulfur, that's this guy. Sodium nitrate, this is the nitrate. The sodium I've left out because the sodium doesn't partake in anything. Okay? Because if you look at the products, it forms sulfur dioxide gas and nitrogen monoxide. It doesn't even appear as a product. Of course it's there, but it doesn't do anything. It's a spectator ion. I can leave the sodium ions out. Okay? Solid sulfur, nitrate, and ions. Product number 1, sulfur dioxide. Product number 2, nitrogen monoxide. So this is just writing down what the question says. Now I have to look at what is taking place. Let's look at the oxidation states of the elements. Okay? Solid sulfur oxidation state 0, because that's the elemental form of sulfur. It has no charge. This is 0. It has oxidation state 0. I have an oxygen here. It's bound to nitrogen. Oxygen must be -2. Okay, so that's -2. This guy has 3. That's a total of -6 that it contributes. The whole thing has to add up to -1. That means this nitrogen here must be +5. Okay? On the other side, this oxygen here, again, 2-. 2 of these guys, that is 4-. That means that this guy is 4+. Right? This oxygen again is 2-, and this nitrogen therefore must be 2+, because the whole thing is neutral. This whole compound is neutral. There's no charges. This is not a polyatomic anion, so this whole thing is neutral. They must add up to 0. Okay, so what is the oxidation that's taking place? Which element is oxidized? The oxygen doesn't change. It's -2 here, -2 there, -2 there. The only thing that's changing is the sulfur and the nitrogen. The sulfur goes from 0 to +. So that one is losing electrons. That's the oxidation step. Okay, so let's write that down. The oxidation step is sulfur goes to this. Alright, now let me try to balance this right away. And it's happening in an acidic solution, so I can use H pluses and water molecules from the solution. Let's do that, and I need that because look, there is 2 oxygens here, nothing here. I have to add 2 water molecules on this side, right? In doing so, I introduce 4 H's, and they appear as an H plus on the other side. 4 of them. So 4 H pluses. Okay, so now all the elements seem to be balanced. Alright, but the charges are not. They're not balanced because there's 4+ charges here. It is 0 overall here. That means I have to add electrons. 4 in total. Okay? Now, there is an extra check that you can do. An extra check that you can do. Namely, this oxidation state changes from 0 to +4. It loses how many electrons? 4 electrons. Ta-da! There they are. Okay? They roll out very nicely. They roll out nicely, by the way, I just want to tell you, this is just, they roll out nicely if the stoichiometric coefficient is 1 here. Okay? If the stoichiometric coefficient would have been 2 here in front, that means also a 2 in front of the electrons, and it becomes 8. Alright, so be careful with that. If it is, as long as it is 1, the number of electrons you generate is really the change in oxidation state of that element. Right? Okay. Let's look at the reduction step. The reduction step must be the nitrogen element that is changing its oxidation state from +5 to +2. Let's write it down. Nitrate on one side, on the other side, nitrogen monoxide. There we go. Let's balance this. First, the number of elements. The nitrogen is balanced, so that's good. Oxygen is not. I need 2 waters on the right side, on the right-hand side. Okay? In doing so, again, I introduce 4 hydrogens. They appear in the form of H plus on the reactant side in this case. And in doing so, I've balanced all the elements. I've not solved the problem of the charges because this 0 charge overall here, 1-, 4+, that's a total of 3+. It needs to be 0. That means I have to add 3 negative charges, 3 electrons. Okay? Quick check, once again. 3 electrons. Does it make sense? Yes, it makes sense. +5, +2, the difference is 3. Okay? And the stoichiometric coefficient is 1 here, so there should be a 3 appearing right there. An extra check you can apply, you don't have to, but you can train yourself to look out for those little opportunities of checking yourself. Okay, so now I've balanced both of these guys, but not relative to one another. So I have to multiply the first one by 3 to get 12 electrons, and the second equation by 4 to get 12 electrons here as well. I had 4 here originally, I had 3 here, so multiply this whole thing by 4, this equation by 3, and that allows me to add up those two equations and cross out the number of electrons. So if I do that, if I add these guys up, I can cross this one out, I can cross this one out as well. So what I see is this: sulfur, 4 times a nitrate anion, 4 H+, there's 3 SO2s, 4 nitrogen monoxides, and 2 water molecules, including their phases. Okay? You can quickly check yourself if everything is okay. You can count the number of elements. There's 3 sulfurs here, 3 sulfurs there. There's 4 hydrogens here, and the number of oxygens also comply. Finally, you want to check the charges. 0 charge here overall, +4, 4 minus, also 0 right there. This must be right. Okay? You can check yourself. You can convince yourself that your answer is correct. Okay? So when it appears correct from all kinds of angles, you don't have to look at it anymore. You can move on to another question.
How did you know not to put sodium in there again?
Why don't I put the sodium ions in there? Because they are spectator ions. You can add them if you want, but they don't partake in the reaction whatsoever. If you add them on the in the beginning, if you add them on the reactant side, you also have to add loose sodium ions on the product side to balance it out.
Are they always spectator or just
In this question, they are spectators. Yeah, because the question says the products are sulfur dioxide and nitrogen monoxide gas. It doesn't say anything about sodium. The only thing a sodium can do is something non-specific to sit there. Yes. Yes, you have to subtract the waters if they appear on both sides. Do that here. There's no water on the left-hand side, so I don't have to do anything. There's also no H pluses on this side, so this is fine. Okay? But yes, if water appears on this side and this side, you cross them out in such a way that the number of water molecules that appears double is taken out. If you had 4 here and 2 there, those 2 go away and 2 are left with the other side. Okay, now let me give you some examples that were taken from actual exams that your predecessors wrestled with. Okay, so here we go. This looks a lot like a precipitation reaction to me. 2 solutions, typical kind of question. Solution number 1, what is given is a volume and a molarity. And solution number 2, again, a volume and a molarity. You put those 2 things together, and something is going to participate. The first part of the question is again very typical, is you have to write down the reaction. And this is something you should be able to do. Okay? First, recognize what calcium bromide is, and be able to write down beryllium sulfate, and then identify the precipitate and balance the equation. Okay? So here it is. They want you to do this in the complete ionic form. Calcium bromide fully dissolves into ions, so it forms calcium 2+ and 2 bromine ions. Beryllium always has charge 2+, sulfate always 2-, so there's 1 beryllium, there's 1 sulfate. What is going to precipitate here? Well, it is not beryllium bromide, okay, because that dissolves very well. But the sulfate and the calcium, they form a non-dissolving pair, and so this is the precipitate. Calcium sulfate is the precipitate, and that's why it has an S here. The beryllium and the bromine are still happily in solution. This is the proper way of writing it down. Okay, with the phases, with the charges, ions that are ions have charges. Ions have charges. Okay? Some people tend not to write the charges of an ion. I don't know why that is. But an ion is an ion because it has a charge. If you don't write the charge, it is not an ion. Okay? It is a neutral compound, which is something completely different. So write those charges. Okay, then, again, a quintessential question for you. How many grams of the precipitate is formed? I have to know how many grams of this stuff do I have. What I have to do is determine the limiting reagent, take the limiting reagent, amount of moles, convert it to the amount of moles of the product, and then convert the moles of the product into grams of the product. That's the step. First step, first order of business, is determining the limiting reagent. Is it calcium bromide or is it beryllium sulfate? That's the question. How to do it? Compare the actual mole ratio with the balanced mole ratio. Okay, the balanced mole ratio is this guy, calcium bromide, over beryllium sulfate, and that is 1 to 1. Okay, that's what the reaction says. The reaction says for each calcium bromide, you need 1 beryllium sulfate. The fact that they're split in ions doesn't matter. Okay, this is still calcium bromide. This is beryllium sulfate, and they react 1 to 1. So the balance ratio is calcium bromide over beryllium sulfate equals 1. The actual ratio comes from this, right? The actual number of moles of calcium bromide over the actual number of moles of beryllium sulfate. You multiply volume by molarity. There you go. This is for calcium bromide. This thing here, the denominator in this case, is beryllium sulfate. That ratio turns out to be 0.67. This is less than 1. This 1 over here. That means that this numerator is the limiting reagent. Calcium bromide is the limiting reagent. I usually write this, LR, which is limiting reagent. Okay? Okay, so take the limiting reagent, the amount of moles of limiting reagent, just calculate it right here. That's where it is. Okay? This is the number of moles of calcium bromide. Convert that into number of moles of the product. How? Through the mole ratio. For each 1 mole of calcium bromide, I have 1 mole of calcium sulfate. So that's 1 to 1. Now I know the number of moles of calcium sulfate, which is the product. Only last step I have to do is to multiply that by the molar mass of it to find the number of grams. Okay, so this is the molar mass of calcium sulfate, the product, and I find, in this particular case, 14 grams of calcium sulfate. Why is it 14? 2 sig figs, because look, it's two sig figs here. All multiplication, so I need 2 sig figs. The answer is therefore 14 grams of calcium sulfate. This is not written in scientific notation that way. That's not a major offensive mistake. That's very minor. For numbers like 14 or whatever, you don't have to do that. As the numbers become really big, then you are advised to write in scientific notation. Okay. Look at the way this is set up. Okay? Balanced ratio, actual ratio, limiting reagent, mole of limiting reagent, ratio, molar mass, done. It's clear, it's easy. This helps actually the grader a lot by giving you partial credit. In the case you made a mistake somewhere here, you can still get points. Okay? So if you can try to do it this way, again, you are enhancing your own chances of getting a higher grade because you get more partial credit. More likely to get some partial credit. Okay. Another one, write the balanced net ionic equation, including states, of the reaction of this. Solid magnesium hydroxide with aqueous hydrobromic acid. This is a acid-base reaction. I'll give you the answer straight away. Okay? This is magnesium hydroxide. It is reacting with hydrobromic acid, which is HBr. Okay? But they asked the net ionic equation. The Br is not doing anything. It's a spectator ion, so I can leave that one out. And just leave the H+. I have 2 waters that form because I have 2 OH minus. 2 OH minus from the magnesium hydroxide. Needs 2 H+ forming 2 waters, and the rest ion is magnesium 2+. The magnesium appears in this net ionic equation because it is bound to the hydroxide as a reactant. That's why it appears. Okay? If this would be fully dissolved, if this, for instance, would have not been magnesium, but barium hydroxide fully dissolves, then you don't have to write the barium. But since it's magnesium, it binds, forms a solid, you leave the magnesium in there. Okay. Second part. How many grams of this salt magnesium hydroxide do you need to completely neutralize 30 milliliters of a certain solution of hydrobromic acid? So this is the reaction we're talking about. I have a bucket with hydrobromic acid in it. It's an acidic solution. I have to keep adding magnesium hydroxide to it till it neutralizes. In other words, there's a couple of H pluses in solution. I can calculate how many. Volume, molarity, I can calculate how many H pluses there are. Those are the H pluses that have to be compensated by adding the same amount of OH minus to it. Okay, so what I want to do is, I want to see how many of those H pluses do I have. Volume times molarity, be careful, milliliter right here, so this is in terms of liters, 0.030 liters times the molarity equals this many moles of HBr. Each HBr delivers one H plus. Okay? So if I take that number here, I can convert that in how many moles of this stuff I need to neutralize all the H pluses. This is the number of H pluses. So what I need is, for each 2 moles of H, I need 1 mole of magnesium hydroxide. 1 to 2. 2 here, 1 there. See that? 1 here, 2 there. Because each magnesium hydroxide is 2 OH minus. Okay, so with 1 magnesium hydroxide, I can neutralize 2 HBRs. That's why there's a 2 there. That 2 is that stoichiometric coefficient right there. This 1 is the 1 in front here. So I'm converting the number of HBRs into the number of magnesium hydroxides. Now I know the number of moles of magnesium hydroxide, multiply that with the molar mass, and that's the answer, 1.36 grams of magnesium hydroxide. Therefore, 1.36 grams of magnesium hydroxide is the right answer, and that will get the full amount of points in this case. All right, very good. Let me give you an example of a typical redox question on the exam. Here it is. Copper sulfate is reacting with solid zinc. In an acidic solution, it forms a new solution with zinc sulfate and solid copper. Okay, so now the first step I have to do is to write down the full reaction and identify the oxidation state of each element, each atom. Here it is. Copper 2 sulfate, there it is, copper 2 sulfate, copper 2 plus and sulfate 2 minus, so this is copper sulfate. Zinc, solid zinc, it forms zinc sulfide, okay, and it forms copper, solid copper. Zinc has oxidation state 2 plus. Oxidation state of zinc is almost in all cases 2 plus. Okay, so let's assign oxidation states. This copper has 2 plus. It says it right here. Okay? This oxygen, always 2 minus. This sulfur here, 6 plus. Why? Because this whole thing, sulfate, is 2 minus in total. There's 4 oxygens. Times minus 2 is minus 8. The whole thing has to be minus 2. That means that the sulfur must be plus 6. Okay, zinc, of course, is 0. Zinc here is 2 plus. And the sulfate hasn't changed, right? So the oxidation states are completely the same. In other words, this sulfate anion is just a spectator, doesn't do anything. The copper has changed to oxidation state 0. That's what it says. Because it's solid copper, that means elemental, that means 0. Okay, so this is the right way to write it down. One way, one thing I'd like to point out, is that some people say, okay, there's 4 oxygens here, so I have to write here minus 8 above the oxygen. No, don't do that. The convention is you write the oxidation state of the element, irrespective of how many you have. If you're asked things in this fashion, write down the oxidation state of the atom you have to write down the oxidation state of the element. Don't multiply that with 4. I know there's a 4. I want you to tell me what the oxidation state of the atom is. Okay. Find the two balanced half reactants in this case. Well, this one is not even that complicated. I recognize immediately that this sulfate anion is not really playing any role. It doesn't change its oxidation state. So I don't have to list it necessarily. It's fully aqueous, so I don't really need it. It's not solid. I can just go like this. Zinc is oxidized because it's losing electrons. It goes from 0 to 2 plus. It actually gives up 2 electrons. The copper takes those electrons. Okay, it goes from 2 plus to 0 and becomes solid copper. The sulfate has no role to play, and I can conveniently leave it out. I don't need it. So this is the oxidation half reaction. This is the reduction step. Once you know that, you can just add these guys up. Just cross out these electrons, and you find the following situation. Zinc, copper, zinc 2 plus, and copper S. So again, put those physical states always. I know that Sapling doesn't always do it. Okay, the homework doesn't request you to put the states in, but I find it very unfortunate, so it leads to bad practice. Please make sure you add the states. Okay? Every time you write something, if you add the states, you make things more clear and easier for yourself in the long run. Okay. So this equation didn't really turn out to be that terribly difficult. Any questions, folks? No? I'm going to go home and sleep. All right. I'll see you on Friday.